Directional fields. Sometimes differential equations can be very difficult to solve, and directional fields are going to give us an idea on what possible solutions might be to the differential equation. So the first thing we need to remember is that dy dx defines the gradient of the tangent, so the gradient of the tangent at any given point on our curve. And when we're looking at differential equations here, they could be in the form where dy dx, we're actually taking inputs of x and y into our function. So usually we're familiar with f of x, something like f of x equaling x squared plus x, where f of x shows us that our only inputs into the function are x to give us an output. But it's possible here we can have inputs of x and y to give us our output for the gradient. So an example of that might be the differential equation of dy dx equaling xy, where we can see we've got inputs of x and y to give us our gradient. Now, to come up with a directional field, we need to look at multiple values of x and y and what the gradient would be for those values. So we're going to create a table where we have values of x that go across and values of y that go down, and then they give us our outputted values given x and y. So let's go ahead and create a table using this differential equation dy dx equals xy. So we'll do it for a few values. So let's create our table. We might look at ranging from 0 to 3 for both x and y. I'm going to need a few columns here and a few rows. Now we're going to put values of x going across and values of y going down. So we'll go 0, 1, 2, 3 for x going across. And you might be tempted to start with 0 and go down, but you'll actually find that going in descending order will be better. So let's write these values as 3, 2, 1, 0, and we'll see why that's going to be handy in a second. So now we just need to go ahead and sub-values these values of x and y into our differential equation. So we've got when x is 0 and y is 3, what do we get? So we just get 0 times 3, which is 0. And in fact, when any of them are 0, the value is going to be 0. So we can just go 0s here and 0s here. Now, these are just products. So 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 1 times 1 is 1. 1 times 2 is 2. And 1 times 3 is 3. And now we can go ahead and create our directional field. So we're going to go ahead and draw our xy axis in. And let's mark in 1, 2, 3 for x and 1, 2, 3 for y. Now, what we want to do is we want to show a rough gradient on all of these points. So the reason we put these in descending order, hopefully you can see, is that on the y-axis they come in descending order. So this helps us map our gradients a bit easier. So all of these zeros represent a zero gradient. So we're going to go ahead and on all those points, so the point 0, 3 is here, the point 0, 2 here, the point 0, 1, the point 0, 0, the point 1, 0, 2, 0, and 3, 0 all have a zero gradient. So we're going to draw a horizontal line here showing we have zero gradient at these points here. Now, when we have at 1, 1, we have a gradient of 1, which is a gradient of 1 is a 45-degree angle. So at 1, 1, at this point here, we've got a 45-degree angle gradient here. At the points 1, 2 and 2, 1, we have gradients of 2, so slightly steeper gradients. So the points 1, 2 and 2, 1, we have slightly steeper gradients. So let's draw those in a little bit steeper. At the points let's look at the points 1, 3 and 3, 1. We have gradients of 3. So those gradients again are a little steeper. So we draw them in like that. At 2, 2, we've got a gradient of 4, which is again slightly steeper. At the points 2, 3 and 3, 2, so here and here, we're going steeper again because the gradients are 6. And finally, at the point 3, 3, we've got a steeper gradient again because it's 9. We get something like that. And usually directional fields are in different colors like this, but obviously if you're doing it, you can just do it in the same color. But the point of the directional field is it gives us a rough idea of possible solutions to the original differential equation. So if we can't solve the differential equation, these directional fields, we can map out possible paths at all the points to show us solutions. So looking here, it's looking like possible solutions are taking form of a parabola function when we follow them up. And this gives us a general idea of these possible solutions. Let's have a look at another example. Let's look at dy dx equals minus x over y. So to do this, we need to draw up a table. So let's go ahead and do that. So we're going to do one a bit bigger this time and look at quite a few values. So we're going to take values from minus 3 all the way to 3. So we're going to put our x values across. So -3, -2, -1, 0, 1, 2, and 3. And again, let's go in descending order. So 3, 2, 1, 0, -1, -2, and -3. So we're going to go ahead and sub in values now to fill out our table. So if we do that, we're getting 1, 2/3, 1/3, 0, -1/3, -2/3, -1, 3/2, 1, 1/2, 0, -1/2, -1, -3/2, 3, 2, 1, 0, -1, -2, -3. All of these will be dividing by 0 for y, so they're all undefined. This should be our y values. We get -3, -2, -1, 0, 1, 2, and 3. Here we get -3/2, -1, -1/2, 0, 1/2, 1, and 3/2. Then -1, -2/3, -1/3, 0, 1/3, 2/3, and 1. So we just got all those from subbing in all the corresponding values for x and y. And this is going to let us draw our directional field. So let's draw up our xy axis. We're going to mark in all the necessary points. So we're going from all the way to 3, so 1, 2, 3. And let's go from -1, -2, and -3. Let's go up 1, 2, 3. And down -1, -2, and -3. So again, putting the y values in descending order helps us map out our gradients a bit better. So let's map in all our 0 gradients so we can see they all occur on the y-axis at every point. So we've got 0 gradients all along our y-axis except for at the origin where it's undefined. So we're not going to mark in anything there. Now, all of our gradients of 1 occur on this diagonal. So let's mark all of those in. So gradients of 1 are occurring here, 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 and here. So gradients of 1 all look like this. 45-degree angle in the positive direction because the gradient's +1. And gradients of -1 occur across in the other diagonal. So let's mark all those in as well. In the same color, because they're the same gradient in terms of magnitude. And they'll all be at 45-degree angles the other way. Now next, let's go with gradients of 1/2. So all the gradients of 1/2, well, one occurs at -1, 2. So gradients of 1/2 will be flatter. We have a -1/2 over here. We have another half at 1 - 2, which is a bit flatter, and another one at -1 - 2. That one's -1/2, so it goes the other way. Let's look at gradients of a third. So we have one at -1,3 over here, so it's a bit flatter than the half. We have a negative a third over here at 1,3. It's a bit flatter. Another minus a third at -1, -3. And another positive a third at 1, -3. Let's look at gradients of 2/3. So we have 2/3, we have one at -2, 3. So somewhere in between 1 and a third, so a bit something like that. Another 2/3 at, or -2/3 at -2, -3. So somewhere down here. Another 2/3 at 2 and -3. And another -2/3 at 2, 3. Let's look at the gradients of 3/2. So we have one at -3, 2. That's going to be a bit steeper than 1. We have -3 on 2 at -3, -2. Another -3 on 2 at 3, 2. And a 3 on 2 at 3, -2. Now let's look at gradients of 2 at -2 and 1. Something like that. And another one at 2, -1. And one of -2 at 2, 1. So here. And another one of -2 at -2, -1. And that just leaves us with gradients of 3 at -3, 1. So about there. And also at 3, -1 over here. And gradients of -3 at 3, 1. So here. And finally, the last -3 at -3, -1. And if you couldn't tell already, these look like they're forming solutions to the differential equation that look like circles. So it looks like possible solutions involving circles for our differential equation that would map out those same gradients.